previously, given a quadratic space V over a field F, we have defined a class of isometries on V. Namely, to each vector V0 in V, we have associated to it something called a symmetry with respect to V0. And geometrically, we can think of this as reflection across the orthogonal complement of the span of V0. Our ultimate goal is to show that these isometries actually generate the whole group, orthogonal group of V, the group of isometries of V. In other words, every isometry of V is going to be a product of these symmetries. But for now, to build up to that, we'll prove something simpler. We'll show that if we have two vectors with the same quote-unquote norm, then there must exist a symmetry, or at most product of two symmetries, sending one to the other. In the case when V is regular of dimension greater than 1, then we can always find a product of two symmetries, sending one to the other. And this product then must therefore be an element of the rotation group, O+. But before proving this, let us explain why such a product must be in O+. To that end, it suffices to show that the determinant of each of these symmetry must be -1, so then the determinant of a product of such symmetry must be 1, and by definition that of the group O+, the rotational group, that means that the product of any two such symmetry must lie in this group. So why is this determinant -1? So we'll actually compute it by finding a matrix for this map. We'll choose a basis first. Since V span a regular subspace, no vector in the span of V can be orthogonal to V because the norm of V is non-zero. So we have the following decomposition, right? And so meaning that we can choose a basis of big V involving V and then the vectors that are perpendicular orthogonal to V. Then observe that in this basis, this symmetry tau V just have this matrix. Why? Because remember that this tau V is just reflection across this orthogonal complement. So it fixes every vector in this orthogonal complement. It fixes all of these W, because if you reflect W across the WI across this, you get WI itself. So it fixes all of those and it flip V. So that accounts for this -1 here, and thus the determinant of this symmetry is just -1, as we claim. So that explains why if an isometry is a product of two symmetries, then they must lie in the rotation group because they have determinant 1. Finally, now let's prove this proposition. It's almost saying that if we look at the set of all vectors of the same norm as this norm x of x, then the symmetries act transitively on it, except that it's not quite, because sometimes we need to use product of two symmetries in just one symmetry to get from one of the vector to the other. So let's prove why. Let's start with two vector x and y of quote-unquote the same norm. We want to find a symmetry mapping x to y, but these symmetry are just reflection. So how do we view y as a reflection of x? Well, the natural choice is to view y as a reflection of x across this, right? If y is tau vx, then v should be this, or any vector here along this line. And what is this vector? That is just x minus y. So we see that we can just write y as tau x minus y of x. Except not quite, so there's some problem with this argument. What's the problem with this argument? Well, over here we haven't accounted for the fact that x minus y might be isotropic. It might have norm 0. So this is the answer only in the case when x minus y is not isotropic. So now let's consider the case when x minus y is actually isotropic. Then it's easy to see that now x plus y is anisotropic. It's not isotropic. So we can apply the previous case now, but in place of y, we put minus y. So by the same argument, we see that minus y is just tau x plus y of x. Thus, we have gotten minus y from x. Now we just need to get y from minus y. And how do we get y from minus y? Well, we just reflect across the orthogonal complement of the span of y. So we have that y is tau y of minus y, and so we can get from x to y using two symmetries. Thus, we can always get from x to y using one or at most two symmetries, as claimed. Now, why is it that if v is regular, then we can always get from x to y using two symmetries? Well, if q of x plus y is not 0, if we are in this case, then we already established that. We just need to go back to this first case when q of x minus y is not 0, but q of x plus y is 0, and get from and apply a symmetry to both sides of this that preserves y. Now, which symmetry preserves y? Well, let's review here. We see here that this reflection fixes this x here if and only if the v naught and the x, they are perpendicular to each other, orthogonal to each other, right? So if we pick any w that is orthogonal to the span of y, then this transformation tau w of y must be equal to y, because y and w are orthogonal, as we mentioned. And so we can write y as we can get y from x via two isometries, because the second isometry doesn't do anything. Now, where did we use the fact that v is regular? Well, for this w to be, so for this tau w, the symmetry with respect to w, to be well defined, we need w to be anisotropic, i.e. the norm of w cannot be 0, because in that definition we need to divide by norm. Well, how do we know that such a w exists? First of all, because dimension of v is greater than 1, we know that this orthogonal complement is non-empty, right? And it's a quadratic space, and being a subspace of a regular space, it's also regular. And let's say it has a basis, orthogonal basis, w1 to wn minus 1. If all of these have norm equal to 0, in particular, let's say w1 has a norm equal to 0, then that means that w1 is orthogonal to w1, but it's also orthogonal to all the other wi's, so that means that w1 is orthogonal to the whole space, right? And so that means w1 lie inside the radical of that whole space, so the space is not regular, so that would be a contradiction. So we should be able to find some vector w whose norm is non-zero. This does allow us to obtain y from x using two symmetries. Thus, we have proved that if x and y have the same norm, then we can get from x to y using at most two symmetries, and exactly two symmetry if v is regular of dimension greater than 1.